Okay, so the second part of this chapter is going to talk about the function of the immune system. So we already saw, generally speaking, in the blood chapter, the functions of the cells. And in here, we're going to focus to the cells that are part of the immune system. So that includes the antigen-presenting cells. So this is what the last part that we covered. And these antigen-presenting cells, what they do is present an antigen. An antigen, it's a molecule that it helps for the cells, at least in our cells, to be identified. And then when it's not part of the cells, can be, for instance, in the environment. An antigen will be defined as a substance or a molecule that can activate the immune system. So then these antigen-presenting cells can activate the immune system. It depends on how strange you consider that antigen to be. If it's something that your immune system cannot tolerate, in that case, yes, you will set an immune response. So the neutrophils, they help in the immune system reactions by releasing molecules like hydrogen peroxide molecules or hypochlorous acid that help to kill pathogens. So this release of these molecules is called a respiratory burst. So the neutrophils themselves, they are the first responders of an inflammatory reaction. So they appear first, and then if in this area where you have inflammation, you have bacteria, well, they release these molecules to kill these bacteria. Now, for eosinophils, which is part of these cells that are the granulocytes, they also have molecules that can damage microorganisms, but in this case will be parasites. And these parasites will be paralyzed with the action of these molecules that these eosinophils have. Now, eosinophils in their granules have also molecules that triggers inflammatory reactions that can open up the blood vessels so that the blood vessels release fluids like plasma into the surroundings. So this is part of these then allergic reactions that sometimes happens in some people. Dendritic cells are antigen-presenting cells, and these dendritic cells, they have like a star shape. They have several extensions, and with these several extensions, like it will be like hands and in their arms, they hold antigens and they present it to these lymphocytes so that the lymphocytes can set an immune reaction. Now, these dendritic cells are specific in certain areas of our body, and they have specific names. The names of the dendritic cells that we have in the skin are called Langerhans cells. And then we have dendritic cells in the brain, which is the microglia. Now, the natural killer cells are a subset of lymphocytes. Remember, lymphocytes, we have B lymphocytes, or B cells, that's the other name. You just change lymphocyte for cells. And then we have T lymphocytes, or T cells, and then we have NK cells. NK stands for natural killer cells. And they are like the snipers of our blood cells. So these ones, they don't need to be pre-activated in order to be functional. If they see a cancer cell, if they see something strange in our cells, if the antigens in our cells, they change, or if they see a bacteria or a microorganism, or they see a virus, they directly attack. So that's why they're called natural killer cells. And they release molecules that are called cytokines, just like as any other cell from the immune system, they also release cytokines. They will, with these cytokines, tell other cells, well, we have a problem. We need to destroy these pathogens that exist in our body. So it's a form of communication, it's the hormones. Basically, it's the text messaging of the cells, the cytokines. Basophils, they also are granulocytes, and they also have, of course, these granules with these chemical mediators of inflammation. They are the less abundant type of white blood cells, and they are located primarily in the blood, although they are located sometimes in the mucous membranes, and in the mucous membranes they are known as mast cells or mastocytes. So similarly as with the eosinophils, when they release these chemical mediators of inflammation, you will have an allergic response. So those are cells of the immune system. Now for chemicals of the immune system. So we have proteins that we call the complement system. And the complement system is called complement system because it complements or it helps the cells of the immune system to set a strong immune reaction. So the cells of the the proteins of the complement system are inactive, and they only get activated when you have a pathogen. They are made in the liver, and they are designated with C and a number. There are around a complex of 30 proteins in total, and they can become active, and they can be part of three pathways. One that is called the classical pathway, that basically happens or starts with the binding of antibodies to a particular antigen. There is a process that is called opsonization, in which you coat these pathogens, these bacteria that might have antigens, you coat them with antibodies. And this coating with antibodies helps for the macrophages to go and attack these bacteria much easier. Most of the people loves cake. And then someone can bake a cake, and the cake itself tastes good, but when they basically they use this nice coating, like the frosting, and they even decorate it, that makes the cake more attractive for being eaten. So similarly, the bacteria, when it's coated with these antibodies, makes the macrophages, the cells that start eating the bacteria, makes them much easier to eat these bacteria. So that's part of the classical pathway, attracting antigen presenting cells to the bacteria by coating them with antibodies. Now, in the lectin pathway, you have proteins that are called lectins that binds to the carbohydrates in microbes. So it's similar to the antibodies, but in this case will be lectins. And then the alternative pathway, it is when you cleave this inactive C3 protein to make it a C3b. So that's the alternative pathway. So here are the three pathways. Classical pathway, coating antigens with antibodies that attracts these antigen-presenting cells, and then your complement binds to these antibodies first. And then in the lectin pathway, you have this coating of these antigens in the microbe surface with lectin proteins that will help to activate complement. And then in the alternative pathway, you cleave the C3 into C3b, and then you activate it. No matter which pathway it is, everything ends in the formation of MAC, membrane attack complex. That MAC is going to open pores in the bacteria, and then that bacteria is going to die through lysis. And then in the case of this complement system, also helps to get rid of these viruses that are neutralized by this C3b, and you can also have these macrophages that endocytose these C3b with these antigens. So any questions about the complement system? So if they are made in the liver and someone has cirrhosis, damage to the liver, can someone has more likelihood to have infections due to the malfunctioning of the complement system? Yes or no? Yes. Why? Because the liver cannot make the complement system. A person will have less likelihood to prevent these infections with the complement system. Now for the inflammatory response. So the inflammatory response is part of the innate system, just like as the complement system. So we all born with chemical mediators of inflammation, and we all born with skin. And let's say that someone has a splinter going to their skin, and that splinter has some bacteria in it. So you will have an injury to your skin, and then you will have your mast cells that are going to go into this area together with the neutrophils, and then you will have release of chemical mediators of inflammation. So these chemical mediators of inflammation will open up the walls of your capillaries, and then you'll have release of protein-rich fluid into this area, and then this protein-rich fluid is going to increase the diameter of this area. This is going to be edema. This is one of the first signs of inflammation. And then you will have increased circulation of blood within this area. So you will have increased temperature. So this is going to be leading to redness. That's another sign of inflammation. And then, as this is happening, you will have some nerves there that can sense molecules, that they can bind molecules that they can activate pain. So we have nociceptors, specific nerves that detects the presence of molecules that can lead to pain. So then what are the cardinal signs of inflammation? So cardinal means main. It's going to be edema, tumor, calor would be increased temperature in that area, not necessarily fever, rubor, redness, or erythema. dolor, pain, and loss of function. So all of this edema will help to prevent you from having microbes going into your bloodstream, hopefully, because you will compress the blood vessels there. And then as the blood is flowing more through the area, you will create heat. That's why you end up with this higher temperature in that inflammatory reaction area. And since you stimulate your pain receptors, your nociceptors, you will use less that particular area. Like, let's say that the splinter, it damaged your index finger. Well, I mean, as long as you don't take it out and as long as you have the inflammation, you won't use it. Why? For protection. That's why we have that loss of function. So you don't damage more your fingers, or your finger in that case. So then one of the cells that is going to come into this place, because you will have damaged cells, including your cells and potentially microorganisms, is going to be the macrophages. So after the neutrophils have killed these bacteria, and then after, within the battle, you will also damage some of these cells within this area, then the janitor, which is the macrophage, will come and start eating up these bacteria, dead cells, including the neutrophils. Some of the neutrophils will be attacked by the bacteria, and they will die, or they get damaged. Who's going to take care of that? The macrophages. And then your bone marrow will increase the production of leukocytes. So one of the signs of having a bacterial infection is neutrophilia, having increased numbers of neutrophils. And then if the infection becomes chronic, or the inflammation becomes chronic, two types of cells will increase, lymphocytes and monocytes. So you have lymphocytosis and monocytosis. But signs of acute inflammation will be increased number of neutrophils. So this is erythema in darker skin and erythema in lighter skin, due to hyperemia, basically having more blood flow within that area. So that's all for the inflammatory reaction. Do you have any questions? Okay, now for adaptive immunity. So in adaptive immunity, we have the cells of adaptive immunity, which will be the lymphocytes, T and B. NK cells are part of the innate immunity. Now, T cells are part of the cell-mediated immunity, while B cells are part of the humoral-mediated immunity. So we have a subset of T cells. We have CD4 plus or helper T cells, and we have CD8 plus or TC cells, cytotoxic cells. So CD stands for cluster of differentiation. So this cluster of differentiation are proteins, are antigens that are found in lymphocytes. And they have a different shape, and they can be identified by these clusters of differentiation. So CD4 has these clusters, and CD8 has these clusters. So helper T cells have CD4, and then cytotoxic T cells, CD8. These are molecular markers. If you see them under the light microscopy, there is no way to tell, well, this is a T lymphocyte, this is a B lymphocyte. And out of the T lymphocytes, this is a CD8, this is a CD4. No, they look so much alike. So you have to do molecular studies to know which type. And then for T cells, specifically the cytotoxic T cells, they respond to viral infections and infections in the inside the cells with bacteria. Now, viral infections happens intracellularly because viruses cannot live outside of the cells. So CD8 helps to destroy virally infected cells and intracellular bacteria. Helper, what they do is activate the macrophages and as well activates the B lymphocytes and the T lymphocytes so that you can have a strong immune reaction against all of these pathogens. Also, T cells respond to foreign cells like those ones from a transplanted organ, and as well to cancer cells. So, for antigens, antigens are made out of peptides, but also can be carbohydrates, lipids, or inorganic molecules like metals. Dander, pollen, inorganic molecules can be also antigens. And antigens are also known as immunogens because they help to generate an immune response. Now, in our cells, we have self-antigens. So these self-antigens are not immunogenic. They shouldn't let you to set an immune response. Because if they do, then you will have an autoimmune disorder. And it's a disorder in which your cells attack your own cells. And then haptens are very small antigens, but they are not immunogenic unless they're attached to a protein carrier. So an example, it is urushiol, which is a toxin of poison ivy. So this molecule is oxidized in our skin and then bind to the skin proteins, and that makes it immunogenic. So not everyone is oxidizing this molecule. So in that case, they don't have that carrier, so they don't have that immunogenic reaction against poison ivy. Now, depending on where the antigen comes from is whether you call it exogenous or endogenous. Exogenous antigen is something that it comes from the outside of the body. It can be transplanted organ, something that it is in the environment like pollen during spring days, like poison ivy. That molecule, that antigen is external, is exogenous. And then that might be taken by the cells by phagocytosis. Endogenous antigens can either be a foreign antigen present on a pathogen that lives inside your cells, like in intracellular bacteria, or can be a self-antigen that changes its shape and then becomes foreign, or can be foreign cancer antigens made by a mutation in the DNA, or a foreign viral antigen. And then this virus infects your cell and inserts the material into your DNA, and then it starts making these foreign antigens. Now, not all the cancer cells form antigens. Otherwise, our immune system will detect them and hopefully will find them completely. So you don't have cancer, but I mean, because we don't have foolproof immune system, then we end up with these diseases. So now, what is the response of the T cells, the T lymphocytes, to the exposure of antigens? Well, your cells from the lymphoid line will start dividing the T cells, and then they will go into the thymus, and then in the thymus, you will start challenging these antigens, these lymphocytes with these antigens. And then the ones that destroy the antigens will be mature, and then they will go into the bloodstream to later on go and populate the lymphoid tissues, including lymph nodes. So only the ones that detect these antigens. The ones that they don't detect them, they will be destroyed. Or the ones that consider your own antigens as foreign, they will be destroyed. This is clonal deletion. So what is the response of the T cells to an antigen? So once your cell get in contact with an antigen, you will start synthesizing these molecules that help to present this antigen. So in this case, you will have your DNA that is going to code or transcribe a messenger RNA, and this messenger RNA is going to be formed into a protein. And then this protein is going to be a receptor that is going to be an MHC, major histocompatibility complex. This major histocompatibility complex is going to be, in the case of the T cells, MHC1, class 1, and that is going to bind to the antigens fragments that are going to be brought into this rough endoplasmic reticulum, and then is going to be bound to these MHCs that now they're going to be carried in a vacuole to be presented in this MHC. So that a cell of the immune system can respond to this. So this is what we call antigen processing. So first you have a large antigen, and then it's being broken down into small pieces, and only that big piece, that important piece will go into this MHC1. You go to the supermarket. If you can afford it, you buy a steak. The steak was wrapped around in paper, or was in these little cases that they have. You go to home, the steak is the antigen, and then what do? You take it out, right? And then you only take out the steak, and then you start cooking it. And then you put it in a plate. So the plate is going to be your MHC, and then your steak is going to be the antigen. And you're going to have extra pieces there that you don't need. It will be crazy if you cook the antigen, if you cook the steak, and then you put it back into the container where you got it from the supermarket, and then you put it in the plate. That doesn't make sense, right? So not everything in the antigen is important. Only the epitope the part that activates the immune system. Better illustration. Someone gives a ring to you, is proposing, but it doesn't give you the ring directly. You put it in the little box. In order to let the people in the world knowing that you're engaged, you don't wear the box. And then you say, I'm engaged. If you're sentimental, you keep even the wrapping from the box and you keep the box. But then you put the antigen, you present it, and then people is going to get the attention. So that's antigen presenting. What is important, you present it. So then that's what happened here. This antigen is broken into tiny pieces, and then it's put into this MHC, and then you keep it in the area, in the plasma membrane. So then once your T cell is exposed, so what happens? The T cell responds to antigen exposure. So then in this case, let's say that you have a pathogen. This pathogen is endocytosed by an antigen-presenting cell. Then this phagocytosed microorganism is going to be destroyed by the enzymes that are present in lysosomes in these antigen-presenting cells. And then the antigen fragments now are going to be presented in this MHC2, in these CD4s, T cells, and then you display this foreign antigen. So then you'll have this T cell activation once you have this presenting of these molecules, these antigens, by these phagocytes or these dendritic cells, and then you will interact with different MHC molecules depending on which one it is. So T helper cell, which is a CD4, will interact with MHC2, while the cytotoxic T cell is a CD8 with MHC1. So this T cell, cytotoxic T cell, CD8, is specific for MHC1, while this helper T cell is specific for MHC2. And you have some additional molecules or, well, receptors. Like in the case of T helper cell, you have co-receptors, and same for this MHC, that are necessary for activating. And then once you, no matter if it's MHC1 or MHC2 activation, you will have responses like dividing the cells to form clones of memory helper cells, memory effector cells, of T helper or cytotoxic. Effector will be the one that is going to help to destroy these antigens, while memory will be kept for the next time. Like that's the picture of you, like the memory. Oh, this is the day when I got engaged with the ring there. So now, in this case, we have effects of T cells. So this is a macrophage that basically is interacting with this helper cell. This is an activated effector. So both of them, they are sharing this antigen in the middle with their corresponding receptors. And you have release of cytokines like interleukin-3, interleukin-2, and other ones, maybe interleukin-1, that are going to stimulate, in the case of these B cells, the formation of antibodies. So that's when T cells, the helper T cells can say to the B cells, well, make some antibodies. Or you can activate the T cells to make more T cells, because maybe instead of someone being in contact with few bacteria, let's say 100 bacteria, that person get in contact with million bacteria. In that case, you need more effector T cells to kill more bacteria. Or you can activate macrophages because you already fight this infection, and then you need to pick up more of these pieces of dead bacteria. Or you can activate both helper cells and macrophages. So you have this along with the formation of more helper memory cells. So those are the effects of T helper cells, either release interleukins or activate the proliferation of B cells so that you can form antibodies. The effects of T cells. So the T cells, once they become activated, they will release these molecules that are called perforins, and these perforins will make these gaps in these cells, the target cells, these pores, so that the target cells will leak their contents. So these directly autolyse or destroy these cells, whether they are virally infected cells, bacterial infected cells. The perforins are the ones that they form these pores, and then the enzymes enter and these fragments these cells. So you have to have first physical contact, and then once you kill the cell, you don't have this physical contact anymore. So you detach these T cells. So that's cellular immunity. Destruction of cells or indirectly forming antibodies. Any questions? Now, B cells, basically, they form antibodies. That's the main function. So B cells, remember, they're formed just as T cells in the bone marrow, and then they mature in the bone marrow. So they undergo mitosis, they form mature cells, and those mature cells goes and populate the germinal centers in the lymph nodes. Once they become activated, because they were activated by these cytokines released by the helper T cells, or plainly because there are some antigens available, you will have coating of these antibodies in these cells, and then you will have these MHC molecules presenting these antigens, and then you will have this physical interaction between the helper T cells and these B cells with the antibodies sandwiching these antigens, and then you will form memory B cells and plasma cells. Plasma cells will be large cells that will secrete these antibodies. And these antibodies can bind more antigens, fighting infections in body fluids. So this is humoral immunity. Antibodies are proteins that has two polypeptide chains. One that is long, and it's called the heavy chain, and one that is short, and it's called the light chain. The antibodies, they have a Y shape with two arms, which are this on the top and this stem in the bottom. These polypeptides are held by the sulfide bridges in this region, and this light chain and this heavy chain are held by these disulfide bridges as well in this region. Now, in this constant region, because it's constant, because it's the same no matter which antibody you are considering, we have 5 types of antibodies, you have a place to attach complement system. part of the classical pathway for activation of complement system. Now, at the ends of these arms, you have something that's called the variable region. This variable region is different, not only for antibody classes, but also within the classes of antibodies, you have hyperspecific regions that binds specific antigens. Two keys can look a lot alike, but only one has that specific hypervariable region that opens that specific block. So, lock this block. So let's pretend that this is the same antibody. Let's say this is IgM and this is IgG. Well, I have there an antigen, which is the lock, and from IgM, I need to have a specific key, a specific antibody that binds to that antigen. So let me choose this first key, and let's see if it's a specific. It's not a specific. It looks a lot like this, but I couldn't unlock. And now look at this antibody. So that's the hyperspecificity that is given at this antigen binding site, the hypervariable region. So we have some antibodies that exist as monomers like this, one only. They can be dimers, 2 attached, or they can be pentamers, 5. Most of them exist as monomers. Some, they are dimers, and some of them are pentamers. Like IgM, it's a pentamer, IgA, it's a dimer. Or some of them, they can be pentamers and dimers. So functions of the antibodies will be neutralize molecules. Other ones will be agglutination. So they can clump several molecules at once, like the ones that are used to type the blood. Other ones will be for opsonization to code these antigens. And no matter if it's coding and attracting more easily the macrophages, anytime that you physically bind an antigen with an antibody, you form an antigen-antibody complex, and this is a physical block. So indirectly leads to neutralization. And then you can activate your complement, and then you can stimulate the release of molecules, setting up an allergic reaction. We have 5 classes of antibodies. IgG, it makes the majority of the antibodies in the serum. This is the only antibody that can cross the placenta. So then, in incompatibility between the baby's blood and the mother's blood, like if the mother is Rh negative and the baby is Rh positive, she can have the antibodies preformed, sent into the blood of the baby to start destroying the baby. Those will be IgG. We saw that in the blood chapter, erythroblastoses fetalis. IgA, it's a dimer. It is found in secretions like breast milk, saliva, tears, semen. It helps to protect against respiratory infections, infections in the eyes. And this one is found in breast milk, same as IgG. The colostrum, the first milk that the baby receives when it's breastfed, it has IgG and IgA. So it receives double supply of antigens. Now, since IgG crosses the placenta, and actually, guys, when we're born, we haven't been exposed to so much antigens. We need antibodies to fight infections. So we all born with IgG that our mom gave us. We all had in our bloodstream IgG coming from the mom. And that supply lasts for 9 months. After that, we start forming our own antibodies. And that's why we start basically immunization within the first year to help for the baby to develop their own antibodies. Plus, the baby also crawls and grabs objects, put it in their mouth, etc. And as it's eating, it's getting immunity. But our mom was so generous that gave us our own supply of 9 months of IgG while we mature our immune system. Now, IgM, it's a pentamer. And this one helps to fix complement system and agglutinates erythrocytes and bacteria. I mean, let's say that potentially each of these can hold 2 antigens, each of these monomers. So this one can hold 2 antigens. How many antigens can IgA hold? If a monomer can hold 2, how many this can hold? 4. What about this pentamer? 10. It has 5 arms. 10. So, and then IgE 2, this one 2. Now, function of IgE, it is to basically, what it does when it's bound to neutrophils, mast cells, it can bind antigens. Let's say that this is a mastocyte or an eosinophil. So eosinophils and mastocytes, they are coated with IgE. So this is IgE. If two adjacent, 2 neighboring IgEs bind at the same time an antigen, if they're cross-bridged, you will release histamine. And that leads to an allergic reaction. So if you only bind one antigen to an antibody, but not to neighboring, you don't have degranulation. You don't have release of histamine. Only when you cross-bridge them. That leads to the sneezing, to the runny nose during allergic reactions due to this. So you suppose that the first time that someone get in contact with an antigen, this is called the primary reaction. Second time is the secondary reaction. So if you have a runny nose or start sneezing after you've been around pollen or something around the environment, that's because you already were in contact with this antigen. Now, IgD, it is found exclusively in the surface of B cells, and apparently this one activates B cells. It helps in the activation of B cells. So this is the comparison of what happens during the primary and secondary immune response. So your primary immune response can take between 4 to 5 days to happen. And your secondary response happens between 1 to 3 days. Well, in this case, your secondary response takes less longer than the primary because that's when you already form your memory. And then the peak for forming antibodies, up to 2 weeks for primary response. So it takes you from day first up to 14 days to form the maximum amount of antibodies on the first time of exposure. The second time that you get exposed, it takes you to form antibody between 3 to 5 days. That's why we have the boosters for vaccinations. And then the primary antibody that is formed first is IgM in the primary response, and the secondary response is IgG. Since you're going to go to the healthcare field, more than likely you will be asked to take your vaccination for hepatitis B. They give you your first shot, and then they give you your boosters. If we were about to know if your booster was effective, creating memory in you, what antibody you're supposed to have in your bloodstream against hepatitis B virus, IgM or IgG? Say it loud.
Is it
IgG. So if you have antibodies against IgG, that means that you are immune against B hepatitis. So this measuring of antibodies is called titers. So the duration of the response is up to 3 weeks in primary, 28 days and beyond for the secondary. And this is the levels of antibodies. So IgM appears first, and then IgG. IgG peaks higher no matter what, and if it's primary, secondary, but this is basically high levels in short period of time for memory antibodies, which is IgG in the secondary response. So adaptive immunity works with innate immunity, and then adaptive subtypes work with each other. So cellular with humoral. You form antibodies because you were exposed by an antigen that was attacked by the cellular type. Now, we have a subdivision of immune system based on the activation of the immune system. And where does this immunity come from? And what type of response do you have? So for antibody-mediated immunity, you have active immunity, which means that you make your own antibodies, or passive if you were given preformed antibodies. There are two ways where you can form your own antibodies. Either you were sick with that disease, or you were vaccinated and you didn't develop that disease because you were vaccinated. If you were vaccinated, this is called artificial active immunity. If you had the disease, this is natural active immunity. So active is always making your own antibodies. Natural when you had the disease, artificial if you were vaccinated. Now, for passive immunity, preformed antibodies. Well, there are two ways to get the preformed antibodies. And we all went through the natural passive because we all born with the IgG that our mom gave us. So that's natural passive immunity because she made those IgG for us and then we get them from her. If you were breastfed, of course, you had a second time of natural passive immunity. Now, artificial passive immunity. There are some drugs that has already preformed antibodies that were formed either in a lymphocyte or in an animal, and these antibodies were purified and were given in a shot to you. It can be the tetanus shots that weren't the normal vaccines that you received when you were a child, or it can be an anti-venom, like for snakes or for black widow. If you were bitten by these animals, they can give you preformed antibodies. That's artificial because it doesn't come from a human source. So, putting it all together, someone get in contact with common cold virus. The person will have mucosas being penetrated, part of this innate immunity, because we are born with mucosa. The virus lands in the mucosa, somehow enters into our body, and then we start developing the signs and symptoms of cold. So then you will have neutrophils, macrophages that are going to go fight this viral infection, and then pieces of these viruses are going to be exposed to these lymphocytes by the macrophages, antigen-presenting cells. T helper cells goes and bind these antigens. T helper cells call B cells to form antibodies and call T cells cytotoxic to destroy these virally infected cells and these viruses. So that's the breaching of this innate immunity and this adaptive immunity, humoral and cellular immunity. And then you will form antibodies, immunity, hopefully, against this virus, and you don't get infected again. So that's how we protect ourselves from that. Bacterial infection is similar. You still form antibodies. You will have, especially if it's intracellular bacteria, T cells, cytotoxic T cells that are going to destroy these bacteria, and then hopefully you have a strong immune reaction that helps to fight this bacterial infection. Cancer cells, in this case, it can be the cytotoxic T cells that destroys them, or it can be the NK cells. Part of the innate immunity, NK cells, and part of the adaptive immunity, the cytotoxic T cells. So that's the normal functioning of the immune system. Now, sometimes we can have problems, like hypersensitivity reactions. Hypersensitivity reactions are the allergies that we know of. So we have type 1, in which you will have an allergen that is detected by the B cells. These B cells become activated, secretes IgG that is going to sensitize these mast cells or these basophils, and then it's what I drew there in the board. So you cross-bridge these IgEs in these cells with an allergen, and then you degranulate. So you release histamine and inflammatory mediators. Now for type 1, which is called anaphylactic, we have local and we have systemic. Local is mild, the signs and symptoms. Someone will have runny nose, watery eyes, sneezes, coughs, but nothing else. We have systemic anaphylaxis that can kill the person within minutes. In this case, you have massive release of histamine. And then the blood vessels open up, vasodilate, they leak a lot of fluid out of the circulatory system, so you end up with cardiovascular shock and death. So those were the persons who carry their EpiPen with them. That's type 1, hypersensitivity. For type 2, we have cytotoxic reactions in which you have, for instance, IgM destroying erythrocytes in a mismatched transfusion. Type 3 is immune complex mediated. In this case, IgG can bind to antigens, and they don't let it go. So these antigens and these antibodies go to small capillaries, clog them, and then the neutrophils come and destroy these capillaries. Example is glomerulonephritis due to this type 2 reaction. Type 4 is delayed. It happens 24 to 72 hours after someone got exposed to these antigens. It can be a transplant, or reaction to foreign antigens. So the acronym for the hypersensitivity reactions, the allergies, the classification: acid, and the hypersensitivity reactions, you write it down, the types with Roman numerals. So you have type 1, type 2, type 3, and type 4. Acid, A for anaphylactic, C for cytotoxic, I for immune complex mediated, that voice of mine put people to sleep. D for delayed, like Johnny. Told you, whenever you have sleeping problems, play a video and then. So that's the acronym. Now, we can have exaggerated immune response, but you can have the opposite, which is immunodeficiency. Like AIDS is a type of immunodeficiency. Your CD4s get destroyed by HIV, and then the person will end up with opportunistic infections. So infections by pathogens that regularly do not infect people with immunocompetent reactions, or this can be rare cancer that happens in people with these reactions, like in this case, Kaposi sarcoma. It's cancer in the skin. And here is the type of hypersensitivity reaction that I told you about. Treatment for allergies: give drugs that blocks the enzyme that produces the inflammatory chemicals, corticosteroids, and allergen immunotherapy. And then attack of your own cells with your immune system cells. This is called autoimmune disorders. We have examples like myasthenia gravis. Your acetylcholine receptor is attacked by antibodies. It's like having your own dog and biting you over and over again, attacking yourself. Okay? So that's all for this chapter. Any questions?